We'll be talking in this video we will be talking about some recurrence relation basic things, and it is a series of videos. There will be probably one or two more lectures on this topic. Here in this video we will be talking some basic stuffs, and as we move on there will be some more topics covering in further lectures. So what is recurrence relation? It is basically a sequence with some condition on its term. For example, let's take arithmetic progression. It is let's take there are first n terms in any AP, random AP. Since it is AP, then common difference has to be same, that is A2 minus A1 must be equal to A3 minus A2 must be equal to A4 minus A3. That is, in general, an minus 1 term must be same to some constant. Let's say d is the constant. So for this here nth term is some relation or function kind of thing of previous term and some relation on n. Similarly, it is in case of GP. Let's take n terms in the sequence. Since this is GP, therefore common ratio of A2 by A1 must be equal to A3 by A2 must be equal to A4 by A3. In general, an upon an minus 1 term must be equal to some ratio. For example, R. Let's take R. Obviously n is greater than equal to 2, because we have taken series from A1 A2 till an. Okay, obviously n greater than equal to 2. Now let's come to formal definition of relation. Recurrence relation is basically nth term must be some relation, that is, or any kind of operation of previous terms and n, basically f of some previous terms and n. It is the definition of recurrence relation. Basically this has to be there, and for solving the recurrence relation there has to be some prerequisite things. First one is induction. It basically tells is it is used to prove some condition. For example, let's take you have to prove sum of first n consecutive natural number is n times n plus 1 by 2. So in this case, as there are two forms, strong form and weak form. As per our requirement, we can use any of both. What it tells is, in weak form, assume the condition given is true for n equal to k. If we prove the condition is also true for n is equal to k plus 1, then we prove the condition, and also prove the condition for some smaller values of an. Basically what it is telling is, let's take we have to prove something like sum of first n natural number must be n into n plus 1 by 2. To prove 1 plus 2 dot dot dot, so 3 plus n, we have to prove n times n plus 1 by 2. Let's take we have to prove this condition for any natural number. So what it tells is basically first prove this condition for some smaller values of n. For example, let's prove the condition for n is equal to 1, 2, 3 for some smaller values, and eventually if you put n is equal to here, you will verify that LHS equal to RHS. Okay, and next, to prove general statement by weak form of induction, it tells, let's assume the condition is true for n is equal to k. So it will imply 1 plus 2 plus 3 till k is equal to k times k plus 1 by 2. Now if you prove the condition is also true for n is equal to k plus 1, then we are done. How? Let's say we have proved n is equal to k plus 1, it is also true. It implies if it is true for n is equal to 2, it has to be true for n is equal to 2 plus 1, that is 3. If it is true for n is equal to 3, it has to be true for 4. Similarly, it has to be true for 5, and so on. It will eventually be proved for all natural number. You can take it as practice problem. It is basically weak form. And one more question is there. Sum of first consecutive square, that is 1 square plus 2 square plus 3 square till nth square. You have to prove this n times n minus 1 times 2n plus 1 by 6 for any natural. Same way, prove for some smaller values, take n is equal to k and prove for n is equal to k plus 1. Let's see strong form of induction. Basically it tells is assume, we have covered weak form, let's move on to strong form. It tells assume the condition given is true for n is equal to 1 till some values till first k natural number. If we prove the condition is also true for n is equal to k plus 1, then we are good to go. For example, let's take this question. Let x and y be real numbers satisfying x plus y, x square plus y square and x cube, and this 4 expression are all integer. You have to prove in general x ki power n plus y ki power n is also integer. Basically it is telling that we have 4 expression, x plus y and x square plus y square and x cube plus y cube and x की power 4 plus y की power 4. This all are integer. This all are integers and x and y are real number. You have to prove in general x की power n plus y की power n is also integer. In general you have to prove x की power n plus y की power n is also integer. So what you have to assume is that let's take it is true for n is equal to 1, 2, 3 till k, and you have to assume that you have to basically assumption. This is our assumption, and now we have to prove it is true. It is true for n is equal to k plus 1 also. So in order to prove the given statement, we will assume this and then we will prove it is true for n is equal to k plus 1 also. Okay, so if let's say we have proved this also, hence if we check for n is equal to 1, 2, 3, the condition is given true for 1 is equal to 2, 3, 4. If we prove this condition also, that is k, then k plus 1 must satisfy it, implying 4 plus 1, that is 5 must satisfy, then 5 plus 1, 6 must satisfy, and so on. All natural will satisfy this. You can take it as practice problem. Okay, let's move on. The next thing which we are going to discuss are partial fractions. So as the name suggests, partial means some parts kind of thing, and fraction means something maybe like breaking into some fractions. Basically it is what it suggests. For example, let's take this expression, it has here, and by taking on all the common denominators and all, you will get 18x plus 7, and basically it is telling that take this fraction, and by taking common LCM and all denominators, you will get this. And now this is basically simplifying routine algebra. And now if we are moving from this step towards this step, this is called partial fractions, breaking into some fractions. Basically what it tells is, for example, decompose this into partial fraction. So we can write this as 3x over 1 minus 2x times 1 plus x. If it is in partial fraction, it implies it has to be a upon 1 minus 2x plus b upon 1 minus x. Okay, implying using all the routine algebra, we will get this a plus b plus a minus 2b times x upon this all. Now since 3x, that is this, and the expression we got in numerator this, they both are identical, that is they are exactly same expression, implying their coefficient of x and the constant term, that is a plus b. We can write 3x as 3x plus 0. Now here constant, wait a minute, 3x plus 0, yeah, we can write 3x as 3x plus 0. So here constant term is 0 and here constant term is a plus b. So a plus b must be 0, and its x coefficient here is a minus 2b must be equal to 3. Upon solving, we get a is equal to 1, b is equal to minus 1. Hence the expression got decomposed into this partial fraction, 1 upon this minus 1. And one more quadratic formula prerequisite, if px is ax square plus bx plus c, or where x is variable, then x is equal to this something minus b plus minus root b square sum upon 2a. Basically you can search on Google for its proof if you want. Quite easy to prove. And next thing, power series. Power series is basically expansion of something like that is this. For example, power series basically, let's take this expression 1 upon 1 minus x. This can be written as 1 plus x square plus till infinity time, that is sigma x to the power n is equal to 0 till infinity, and goes from 0 till infinity. It is basically expansion and simplification of this LHS and RHS, basically they both are same, and you can prove it by GP. And where mod x, that is less than 1, that is x greater than -1 and less than 1, this is the main condition for it to be happen. That is, if we are given this, then we can vice versa say it is true for this x, for values of x in this interval, x greater than -1, x less than 1, it will, this expansion is valid. Okay, we have some terms related to recurrence relation. Basically we will define some terms, for that we can study recurrence relation easily. For example, for studying polynomials, we have defined degree, that is degree 2 quadratic, degree 3 cubic, degree 4 biquadratic, and so on. So basically we will study separate for, and the same chronology here, that we will be defining order and degree in recurrence relation. Let's see what are them. Degree is basically order is basically the order of the recurrence relation. an is equal to blah blah blah, an minus 1, an minus 2, till an minus k, and n is k. Basically it is telling that an is depending on which lowest term, that is for example, let's take here, so an is depending on previous lowest an minus 2 term, so it is n minus 2, so it is order is 2. To basically do n minus this, so n minus n cancel, minus times minus plus 2, so plus 2. Similarly an is blah blah something something. Now an is depending on which smallest term, smallest number term, that is n minus 2 and an minus 2, an minus 4. Now n minus 4 is smallest, so you just do n minus this, that is n minus n, it will cancel, minus times minus plus, so order is 4. I hope you got similar, like in this case an is some function of this. Now it is some smallest term, it is depending on n minus k, this is the smallest term on it is depending, so do n minus this, that is n minus n, cancel, and plus times minus plus time, minus times minus plus, and left is k, so it is k. Same thing we applied here, it's n is depending on lowest which term, an minus 4, so n minus this. For example, let's take some more example, like let's take 2an to be equal to some like a n minus 1 plus a n minus 2 plus a n minus 3. Let's take like this expression we got here, minus 2. Okay, now an is depending on previous which lowest term, that is here lowest term is n minus 3, n minus 1, and n minus 2. Among this lowest is n minus 3, so we just do n minus that is n minus this, it is basically 3, so its order is 3, so its order is equal to 3 basically. I hope you got it. Next we have here is and also it's a wrong thing, that the order is not the number of term on which an is depending. I hope you got. For example, if it was this definition, then in this case order must be 2, because the it is depending on this term and this term, that is it is depending on 2 terms, but here order is 4, so it is a wrong definition. Actual definition is an is depending on lowest which term, here lowest is n minus 4, so do n minus 4, that is 4. And degree is basically a recurrence relation, is the degree of an an treated as a polynomial in its variable excluding n. Okay, let's read one more time. The degree of the recurrence relation is the degree of an nth term, okay, treated as a polynomial in its variables excluding n. Okay, basically let's take this example, an is equal to 2 an minus 2 plus n square. Here see, it was given to us something like this, an, I hope it was the same, an is 2a n minus 2 plus n square. An is equal to an minus, okay fine, minus 2 plus n square. Okay, it was this. So here degrees basically treat each anet, that is a subscript, as this as a some variable polynomial, let's say x. It is basically x, and treat this also as x. so it will become x is equal to 2x plus n square. Now see, here the highest exponent of x is 1, so basically its degree is 1. Similarly here, treat each this recurrence term, previous term, as a variable x, a polynomial. So here let's take it as variable x, so x is equal to n square plus 1 times x plus x. So highest power of x here also is 1, so degree is 1. Okay, similarly way. And what is linear? A recurrence relation of degree 1 is called linear. Okay, and a recurrence relation of degree 2 is called quadratic. Yes, a recurrence relation of degree 1 is linear, basically the definition of linear, and a recurrence relation of degree 2 is quadratic, basically some intuitive related to polynomials. Okay, and homogeneous. Basically a recurrence relation is called homogeneous if it contains no term that depends only on the variable n. Well, what it tells, basically let's take this example. Homogeneous means recurrence relation which does not contain any term that depends only on the variable n. For example, let's take this recursion. We have an is equal to something 2an minus 2 plus n square. Now here we have a term basically separated by plus or minus sign, basically. Okay, so it is one term, two term. So this one term is depending only on the variable n, hence it is not homogeneous, because if it would be homogeneous then there won't be this term, but since it is here, hence it is non-homogeneous. Similarly, if we take here, we have a term, this term here, which depends only on the variable n, hence it is non-homogeneous. Let's say if here would not be n factorial, here let's say was not n factorial, let's cancel out here. So now we have left with n square plus 1 an minus 2 plus an minus 4. Now this does not have any term depending on only n, hence it is homogeneous. Basically it is what definition. Okay, I hope you got it. Next we have solution to recurrence relation. What is mean by this recurrence relation? Basically this function of previous term and n, and solution of recurrence relation an is nothing but an to be a function depending on only n. That is, for example, if we take in case of arithmetic progression, we had a n minus a. Wait a minute, let's take another book. In case of arithmetic progression, we had an minus an minus 1 is equal to some constant. This an minus 1 a sub n minus 1 has to be some constant d. Now those who have read arithmetic progression, they must have known that its general term an from here is nothing but an is first term. Wait a minute. Yes, so its first term an, those who have read AP, they must have known an is nothing but first term a1 plus a plus n minus 1 times the common difference, that is d. This is solution. Why it is solution? Because it is depending only on the variable n. Put a is equal to n is equal to 1, a1 is a1 plus 1 minus 1 0, satisfying. Put a is equal to 2, a2 is a1 plus 2 minus 1, that is 1, d. A3 is, put n is equal to 3, that is a1 plus 2d. Fine. This is solution. Here a1 and d are constants. It is depending on n, no previous term is here. Okay, fine.